Greetings all, I'm Wansen from the University of Science and Technology of China. I'm happy here to present the work of our team. Ethereum smart contracts have been widely used. At the same time, they manage users and tokens, which have a high economic value. Unfortunately, it makes Ethereum smart contracts become the target of many attackers. Considering the losses caused by Ethereum smart contracts being attacked, it is necessary to guarantee the financial security of them. By the way, for convenience, I will call Ethereum smart contracts as simply smart contracts or contracts in this presentation. The most popular idea for protecting contracts is to use an analyzer to analyze them before deployment. Current security analyzers of smart contracts can be divided into three categories. The first category, automated bug-finding tools, support automated analysis on a great amount of smart contracts, but their analysis is based on predefined patterns and is not accurate enough. The semi-automated verification frameworks can formally verify the security of contracts, but require manually defined properties and are not suitable for a larger number of contracts. And the automated verifiers try to provide sound and automated verification of predefined properties for smart contracts. To the best of our knowledge, there are three automated verifiers: ESO, Sacrifice, and Zeus. But there are still problems to use them on analyzing the financial security of contracts. Instead, in this work, we target to propose a new automated verifier with auto-generated properties for analyzing the financial security of contracts. Here, we first introduce an example. This example is used to transfer tokens, and the mapping type variable in the line 2 balances. It denotes the token balances of accounts in different addresses. And the function transfer is used to transfer tokens from one address to another address. In normal cases, when this function is invoked, the token balance of message.sender will decrease, and the token balance of 2 will increase. However, consider an abnormal case. If the value of message.sender and 2 is the same address, the result of line 10 will overwrite the result of line 9. Therefore, the token balance of address 2 will increase without the token balance of any other account decreases. As a result, an account can get unlimited tokens by invoking this function again and again. Thus, we can say that this example is vulnerable. And to automatically verify this example and find the vulnerability, there are three questions. How to generate properties to cover the vulnerability, how to translate the source code into models, how to verify the properties against the models. And the first question, automated property generation, is the main challenge of our work. Since there is no uniform standard for the security requirements of contracts, it is difficult to propose general properties for contracts. And most existing automated tools define patterns or properties according to known vulnerabilities. However, it makes their tools limited to known vulnerabilities. To address this challenge, we propose an observation based on our statistical analysis. The observation is most of the contracts are finance related. In other words, related to ethers or tokens. Plus that our goal is to analyze the financial security of smart contracts. So in our work, we focus on ethers and tokens and regard them as the basis of our properties. At first, we propose the categories of contracts according to the cryptocurrency they use. The Ether-related contracts use the official currency of Ethereum, that is Ethers, while token-related contracts use custom tokens, and the indirect related contracts do not use tokens or Ethers, but implement some functions for the former two kinds of contracts. And the remaining contracts are called non-finance related contracts. Then, we propose the method to identify the category of contracts automatically. The Ether-related contracts can be identified by searching for official keywords since the transferring or ethers is done by using these keywords like transfer, send, call, payable, and differently, there is no official keyword for the transferring of tokens. So we propose our second observation, according to another statistical analysis. Most token contracts use similar variable names to denote token balances. We find two common names, balances on the token count. Therefore, we consider a contract to be a token contract if it defines variables or mapping type with names similar to these two variable names. By the way, the identification of indirect related contracts can be done easily after the former two kinds of contracts are identified. Lastly, two kinds of properties are generated for different categories of contracts. The invariant property requires that an invariant hold before and after any transactions of the contract. For example, we give an invariant as follows for the token-related contracts. This invariant requires that the sum of token balances is constant, which ensures that the token balances are calculated in an expected way. And the calculation of ether balance is performed by a Ethereum virtual machine. So we assume that the calculation is correct, so we do not provide invariant for ether-related contracts. Note that this invariant can also be provided by the users of our tool. And the equivalence property is provided for ether-related contracts and token-related contracts. This property requires that given two sequences A and B consisting of the same transactions, the token balance and the ether balance of the adversary are the same after the execution of A and B, regardless of the orders of transactions in the sequence or any other conditions. If this property is violated, it means that the adversary may change its own balances by modifying some conditions. Recall the previous example. We can see that the vulnerability is covered by our invariant property, while the sum of the token balance is changed. However, in our evaluation, we find that this vulnerability cannot be detected by our other automatic tools, which indicates one advantage of our properties not limited to known vulnerabilities, since our properties are not generated according to any patterns. Besides property generation, there are also questions about modeling and verification. For automated modeling, since the equivalence property requires reasoning on multiple executions, we propose a two-step method to generate different models according to the invariant property and the equivalence property respectively. Besides, we prove the soundness of the translation from the Solidity language to our models based on a custom semantic of Solidity. Also, we implement the automated verification by modifying the source code of Tamarin prover and adding additional support for numerical constraint solving use these three. Finally, we introduce the evaluation of our tool. We use two datasets here. The first dataset is used to test the performance of our tool in detecting different types of vulnerabilities. This dataset is collected from several public datasets of other works. And the second real-world dataset is used to evaluate the effectiveness of our tool in detecting real-world smart contracts. This dataset is collected from EtherScan. We first perform some statistical analysis on real-world dataset. We manually classify the contracts and find 27,858. This result corresponds to our first observation. Most contracts are finance related. And recall that our second observation is that most token contracts use similar names to denote the token balances. So we manually identify the token contracts and compare the result with the token contracts identified by our method. As a result, we find that our method can achieve accuracy higher than 98%, and this result not only validates our second observation, but also shows the effectiveness of our method to identify token contracts. Then, we compare our tool with other automatic tools on vulnerability dataset. Totally, our tool achieves higher accuracy and F1 values than other tools. Meanwhile, the transfer mint vulnerability, in other words, the vulnerability in the previous example can only be detected automatically by our tools. We also use our tool to analyze 1,700 real-world contracts. And the result, we find 10 contracts with transfer mint vulnerabilities and 3 contracts with time step dependency. And these contracts are still online on the Ethereum. Besides, our tool still has several limitations now. Our team is still working on this tool and will make a further research trying to solve the above limitations. Thank you for listening.